All right. So we're going to take a look at section 4.3. And this is what we call the first derivative test. And what we're going to be looking at, we're looking for ways of finding local extrema. So let me just kind of review a little bit about extrema. We've seen this earlier. But we're going to have something, say, like a function that does this. And take a look at this function. And let's say it's asymptotic, has a horizontal asymptote, or maybe a slightly oblique asymptote. We better make it horizontal. Let me go back here. So let's give this thing a horizontal asymptote like this. So we know that it's going to just kind of get closer and closer to the line as we go this way, closer and closer that way. But it's just going to do this sort of smoothing out behavior. Well, this is the highest point on this entire function. So we would call this the absolute max. And this is the lowest point on the entire function. We can call this the absolute minimum. And taking a look at this, this is a high point, but it's not the highest point. So we can call this a local max. And we've got another local max over here. And then we have a local minimum. It's not the lowest point, but it's just a locally low point. And so these are the extrema of our function. And what we're going to try to do is we're looking for ways to identify these extrema. And one of the methods that we're going to use a couple methods today. We're going to talk about the first derivative test and the second derivative test. And first off, it's going to introduce some terminology. So a function is monotonic on an interval if it is always increasing or always decreasing on that interval. So we're going to use a property of first derivatives to help us identify when a function is increasing or decreasing. So to do this, we're going to use our derivative. And if we think about this, what we're going to see is that when you have a function with tangent lines that have positive slopes, then that function is going to be increasing. And if the tangent lines have negative slopes, then the function will be decreasing. So let me draw a picture just to illustrate what that looks like. So if there's an increasing f of x, the tangent lines have positive slopes. Or f prime of x is greater than 0. So when we think of an increasing function, we're thinking of increasing from left to right. So let's say we have kind of an arc like this. Functions doing this. Then if we look at the tangent lines, they're all going to be lines with positive slopes. So that tells us this function is increasing. In other words, we can just look at f prime of x, and since it's greater than 0 all along this arc, this tells us f of x is increasing. Now, let's look at decreasing f of x. Here, the tangent lines have negative slopes. Or f prime of x is less than 0. So again, let's take a look at an arc. And again, we judge increasing and decreasing as we go left to right. So if we take a look at the tangent lines, and they have slopes that are equal to the derivative at this point, a little more line-like. And again, we have one here. The tangent lines have negative slopes. So we're going to sum this up like this. And this is going to be a corollary to this idea of increasing and decreasing functions. As if I'm erasing too fast, please let me know. So suppose f of x is continuous and differentiable on, oh, let me back up here. Skip the key thing. Pardon me. We want f of x continuous on a closed interval and differentiable on the interior of that interval, which is the open interval AB. So you have two parts to this. If f prime of x is greater than 0 at each point, in the open interval, then f of x is increasing on the closed interval. And then to go with this, if f prime of x is less than 0 at each point, in AB, then f of x is decreasing on the entire closed interval. So where's this going with extrema? Well, what we're going to be looking at is when we think about finding a maximum or a minimum, it's like climbing up a hill. If you climb up a hill, eventually it's a tough go. I mean, it's steep and you're getting kind of tired. And then you hit the top and you can rest, and then you head downhill and it's kind of easy coasting from there. So what this means for finding extrema So let's say we have C here, and this is the top. And remember, when we get to the top or the bottom, we have f prime of C is equal to 0. In other words, in fact, let me draw this so we're pointing more at the exact location. Here, the horizontal tangent line, it's flat, so there's a slope of 0, and that means we're at the top of a hill. So along here, f of x is increasing. And here, f of x is decreasing. And if we look at those tangent lines, we have a positive slope for an f prime of x is greater than 0. And then here, where it's decreasing, if an f prime of x is less than 0. So what we might start to see is this. As we go from left to right, in this particular case, the derivative is greater than 0, then the derivative is 0, and then it's less than 0. So let's take a look at our derivatives. We'll have plus, 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 0, and then minus, 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 minus. And so this is f prime of x. This is what f prime of x is doing. So what we're seeing is that when we have really a hill with a top, our derivative will start out positive, then it'll hit 0, and then it's going to go negative. So any questions, and we're going to do some examples with this, but any questions about this? And we'll summarize this. We're going to come up with what we call the first derivative test. All right. So here we have another kind of local extrema. Here's a local min. And again here, there's our C, and there's f prime of C equals 0. And then along this way, f of x is decreasing. Here, f of x is increasing. And if we look at derivatives, we've got tangent lines with negative slopes. And here we have tangent lines with positive slopes. So for this minimum, we take a look at our derivatives. First derivative, we have minus, 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 0, plus, 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 plus. And this is what f prime of x is doing. So when we have a minimum like this, our first derivative is negative, then 0, and then positive. So we're going to summarize this as what we're going to call the first derivative test. It's going to work like this. And this is going to be a test that for this section and the next section, we're going to hang on to. Because ultimately, we're going to try to draw these graphs with the help of our derivatives. A little like what we did in college algebra. So here's sort of the first sort of big test for this chapter. our first derivative test. Now, we're going to suppose that C be a critical point. Oh, I forgot to actually put the C there. Now, critical points and just to review what critical points are, this means that f prime of C equals 0, which is what we've looked at so far this afternoon, or f prime of C is undefined. So that's what our critical points are going to be. Now we're going to suppose f of x is continuous and differentiable on an open interval containing C. And again, when we talk about functions increasing or decreasing, we're going to be moving across the open interval from left to right. And as we do this, we're going to look for something. I'll give you a second here to copy that down. All right. So let's take a look at the setup. We're looking for critical points. Now, this is where the derivative of f is 0 or where it's undefined. And that's the derivative. And we want to work on an open interval where f is continuous and it's differentiable at each point in this open interval. And this open interval contains, say, the critical point C. So as we're moving from left to right, what are we looking for? If f prime of x changes, almost launched into cursive there, from negative to positive at C, f of x has a local min at x equals C. And that was that second example that we saw with the downward or the well, sort of the smiley face looking arc. So what that means, if you look at your first derivative, you'll have negative, 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 0 at C, positive, 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 positive. And again, that's your f prime of x. So that tells you have a local minimum at x equals C. So any questions about that? All right. Now the second part, if f prime of x changes from plus to minus, then f of x has a local max at x equals C. So again, if we kind of take a look at that first arc, there's C. Well, we're going to see positive, drop down a little bit lower, positive, 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 0, minus, 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 minus for the f prime of x. So any questions about that? All right. And then finally, the third point with this first derivative test. If f prime of x does not change sign, at x equals C, then f of x has no local, or absolute for that matter, extremum at x equals C. So a function that might produce something like this, you have a function that kind of does this, and then for a second levels out, continues up. Like you could kind of something like f of x cubed, for example, behaves this way. So we could have a horizontal tangent line like this, where f prime of C equals 0. We could have something like this. And then we have a horizontal tangent line. Or not horizontal, I'm sorry, just a tangent line, or f prime of x. That's a tangent line with a positive slope. So that means the derivative is greater than 0. But on this side over here, we're going to see the same thing. Yeah, plus, 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 0. But then we keep going plus. There's no change in sign. And this is not a minimum or a maximum of any kind. So that's how that third case can come in. Now, any questions about that before I do an example? All right. So let's say we have something like this. So first off, what we're going to do, let's find the critical points. So this is something we looked at last time. We need to calculate f prime of x. And we've got a function times a function. We would use the product rule. And just for the sake of time, I'll just put the result here. But what we're ultimately going to get is x squared plus 2x minus 3 times e to the x. Now, if we take a look at this, there's no value of x. It's going to cause f prime of x to be undefined. So we don't have to worry about that. Like, we're not going to get a division by 0. We're not going to get the square root of a negative number. We don't have to worry about taking the logarithm of 0 or a negative number. We're okay. So what we're going to look for is f prime of x is equal to 0. Now, one thing to point out, this is never 0. So we can divide both sides by e to the x just to get rid of it. It's never going to be 0. So we can just sort of eliminate it that way. And so we'll get 0, x squared plus 2x minus 3. Or we can factor this, x plus 3, x minus 1. Or that means x equals minus 3 and x equals 1. So this is what we can do. We have our critical points. So in this case, we have 2 c's to work with. So we want to take a look at what does f prime of x do around these critical points. So what we're going to do, we're going to use test points. Now, what x being -3 and x being 1 means, again, this tells us where the derivative is 0. So this divides the x-axis into intervals. And we want to see what's going on in each of these intervals. Now we know when x is -3 or when x is 1, the derivative is 0. This is our f prime of x. So what's going on here, here, and here? Well, these are going to form the open intervals that we want to look at. And they're going to be open because we're not going to include -3 and 1 because we already know what the derivative is at these points. Excuse me. So I'm going to choose some pretty, what I think are easy test points. I'm going to choose, say, 0. Let's choose, say, 2. Let's choose, say, no, maybe not terribly easy, but say -4. In fact, let me put these above so these are test points and not to be confused with the boundaries of our intervals. So you have our test points, -4, 0, and 2. And so what we're going to do, let's look at the derivative at x is -4. Well, f prime of -4 is going to be -4 squared plus 2 times -4 minus 3 times e to the -4, which approximately, let's see here, grab a calculator real quick. It's going to be, well, no, it'll be 5 times e to the -4. And the moral of the story here, we don't need to go through, I'll go through the calculation. We don't have to actually go through with it. We just need to know if the result is going to be positive or negative. It's going to be a very small positive number, 0.916. But the key thing is it's greater than 0. So that means we're going to consider this entire interval containing -4 to be positive. Now, how do I know the entire interval is positive? Well, remember, it can only go from positive to negative if it becomes 0 first. The first derivative can only go from positive to negative if it becomes 0 first. So when we know where it transitions, and it's going to be where the derivative is 0, well, that means everything up to this point has to be the same sign. And then, and only then, if it's going to switch signs, it's going to do so after it becomes 0 first. Positive numbers and then 0, then maybe negatives. We'll have to see. So we know that this is going to be positive. Now let's take a look at the next one. X is 0. So f prime of 0, 0 squared plus 2 times 0 minus 3 e to the 0. Well, let's see, this will be negative 3 times 1. E to the 0 is 1. So we're going to get negative 3, and that's less than 0. So again, this entire interval is going to be negative, and for the same reasons. You can only go from negative to positive if you transition through 0. And so that's going to mean that until we hit a 0 and then change over, hit a 0 and possibly change over, we're going to have the same sign. Now, any questions? Now, there are some situations where, let's see, you could come up with a function that doesn't work quite that way, but you're going to have, let's see, we'll have to play around with that. You're dealing with points where the derivative is undefined, but that's another story. We'll take a look at something like that in a little bit. Finally, for x equals 2, f prime of 2 is going to be 2 squared plus 2 times 2 minus 3 e to the 2, or let's see, we'll get 8 minus e is 5 e to the 2, and again we'll approximate this. The key thing is bigger than 0. So that means this interval has a positive derivative. So let me redraw my intervals then, like so. So we found out first derivative is 0 at these two locations. Using the test point of negative 4, f prime of negative 4 was positive. So that means this whole interval has positive first derivatives. Then we use 0 as a test point in this interval, and we found out f prime of 0 was negative. So we're going to have negative for that interval. And using 2, oh, I'm sorry, that's a positive one. Ooh, my bad. Positive 1, not negative 1, positive 1. Using 2 as a test point, we got positive again. So by the first derivative test, what we're looking at is something that looks like this. And here, we have something that looks like this. So by the first derivative test, abbreviate derivative, x equals -3 is a local max, and x equals 1 is a local min. So any questions about that? So one thing to kind of keep in mind, we could get a function, say like this. For example, f of x equals 1 over x squared. And if we take a look at the tangent lines, here f of x, f prime of x is greater than 0, f prime of x is less than 0. So, and then if we take a look at, say, 0, we have our x equals c equals 0, we'll get f prime of 0 in this case is going to be undefined. So it is a critical point. So I just want to point this function out. So if you do f prime of x, your d dx of 1 over x squared, or d dx x to the negative 2, what you'll get is negative 2 over x cubed is what you're going to have. So just kind of something to point out here, we're not looking at a local max or a local min per se at this point. That's something that you want to just kind of be aware of. And that's something that we can talk about later. I just kind of warn you about this function. You're not going to get the that peak that we're used to. And the reason is we're going to have a vertical asymptote coming right down the middle here to begin with. And one of the key things why this isn't working is, again, we want to go back to the setup for the first derivative test. We require f of x to be continuous on the open interval containing x equals c. And here at the vertical asymptote, that's going to be a discontinuity. So just keep that in mind. So if you kind of jump into this, you want to make sure that you meet your prerequisite that you have that f of x is continuous and it's differentiable on an open interval containing our x equals c. So just to kind of put that out there. All right, so any questions about that? All right. So that's section 4.3. Now, why are we interested in these kinds of things? What happens if you're looking at some relationship, if you establish a relationship between two quantities, say temperature and like the breakdown of, say, a rubber gasket, for example, and you're looking at or maybe not that might be something that's a little more consistent, but you can use these to find your maximums and minimums. You might be looking to maximize profit, you might be looking to maximize area, and when you have a relationship between, say, area and then, like, say, the dimensions involving x, you can use this to find your maximum area. And so that's why we're so interested in finding these maximums and minimums. And we're going to get to a section in chapter 4 about that. Now, first off, let's go into 4.4, and we're going to kind of get into this a little bit more. Concavity. And so the way we describe concavity is this. F of x is concave up on interval I. If f prime of x is increasing. On I. So we're not talking about f of x, we're talking about f prime of x. And then we're going to say that f of x is concave down on interval I if f prime of x is decreasing on I. I'll go over some illustrations as what does this mean. So we say f of x is concave up based on what f prime of x is doing, and that's if f prime of x is increasing. And then we say f of x is concave down if f prime of x is decreasing. So let's talk about what does it mean for f prime of x to be increasing or decreasing. So what does that actually mean? So what it means is this. F prime of x increasing. This means the tangent slopes they're increasing. So to give an example, this might seem kind of silly at first, but then you'll see what I mean. Maybe you won't find it silly. But let's take a look at these 3 points. Look at the tangent slopes. Well, this tangent slope, barring artistic license, this is a negative tangent slope. And then this tangent slope is 0. And then at this tangent slope, it's positive. So f prime of x is negative, then 0, and then positive, where it's increasing. Ooh, squeeze the word increasing in there. So this is what we mean by concave up. And here, I'll put a colon here. I think that makes a little more sense. So you go from, say, negative to 0 to positive. That'd be an example of concave up. Now, it doesn't have to go from negative. It just has to be increasing. It can go from 0 to positive. That's okay as well. It doesn't have to be all the way from negative to 0 to positive. But it could go from like 0 to positive, or even from slightly positive to very steep. That would be concave up as well. Now let's take a look at f prime always decreasing. Well, use kind of a here. Let me put in my tangent slopes. Tangent slopes that's what's decreasing. So, example of that. Well, here, the tangent slope is positive. And here, the tangent slope is 0. And here, the tangent slope is negative. So in this case, if you look at our f prime of x, went from positive to 0 to negative. And this is what we mean by concave down. Now, again, it doesn't have to go from positive to 0 to negative. It just needs to be decreasing. It doesn't actually have to have a transition in sign, but it just needs to be decreasing. So you could have a slightly negative and then a much steeper negative slope, and you're still dealing with concave down. And I do want to make one note on this interval I that we've been talking about. I didn't mention it already. We work with interval I is open. Let's make sure we get that in there. So what we're going to come up with is the second derivative test for concavity, and that's going to segue into the second derivative test for extrema. Now you might be thinking on this, if we're looking at concavity, it's kind of giving a hint about maximums and minimums. But this is what we're going to do to help identify the kinds of concavity. If f double prime of x is greater than 0 on this open interval I, the graph of f of x over I is concave up. So we're going to get some help from the second derivative. If f double prime of x is less than 0 on I, the graph of f of x over I is concave down. So a key thing here, if the second derivative is greater than 0 at every point in this open interval I, then f over this interval is concave up. But if f double prime of x is less than 0 at every point in this open interval I, then f of x is concave down over this interval. So let me just do a couple sort of, hopefully not too complicated examples. Let's go with one that we're a little familiar with, or parabola. So if we take a look at a graph of our parabola, we're going to see it does something like this. And if we take a look at the derivatives, or the slopes of the tangent lines, we have negative, then we have 0, so they've increased, and they're going to be increasing. So if we take the derivative of this, f prime of x is going to be 2x. And then f double prime of x is equal to 2. What we get is that f double prime of x, since it's positive 2, it's greater than 0, really on any open interval So this means f of x is concave up on any open interval. Well, yes. Questions about that? All right. Now, if we do another example, let's say we have this, negative x squared. If we graph this, you get something that looks like this. So this is a positive tangent slope. There's a 0 tangent slope. And there's a negative tangent slope. And again, we're looking as things go from left to right. So f prime of x is decreasing. So that means this is concave down. And if we take the derivative, we get negative 2x. Take it again, we get negative 2. And so, since f prime of x is less than 0 on any open interval, then f of x itself is concave down on any open interval. Now, when we're looking at these two examples, we're sort of seeing something here where if a function is concave down, it's going to have a local max. But when it was concave up, it's going to have a local min. And that's where we're tying this together with extrema. So what we're going to do, we're going to make this observation. We're going to look for what's called an inflection point. And the best way to describe this, it's where the concavity changes for a function. So what this might look like, if we have like a max and then we have a min, local max and local min, there's a transition somewhere in here at some point. And this would be an inflection point. So what this says is here we would have concave down. And then from over here, we'll have concave up. So where you get that transition from one point of concavity to the other, that's going to be your inflection point. And so what we can do, we can go back to the second derivative test. And what we can say, we can use it to a point. We can say this. At an inflection point. One of two things is going to happen. F double prime of x equals 0, or F double prime of x doesn't exist. So why would it turn out this way? Well, we want to think back to our second derivative test for concavity. What that says, let's say we have, and since we've used C for critical points, they're going to use C again for concavity, or inflection points. So I'll stick with the convention. I'd be tempted to use a different one. But let's say we have concave down, and then we have concave up. And we're talking about F double prime of x. We're going back to that second derivative test. Well, if we're concave up, the second derivative is greater than 0. So we're going to have something like this. If we're, concave down, it's less than 0. Sorry. It's going to be negative. And if it's concave up, it's greater than 0. So our inflection point, we're going to either have 0 or non-existent. So that's what we're saying. When we look at the F double prime, where it's negative or concave down, it's positive or concave up, and then at C, where it's transitioning, that's when we're going to get our inflection point. So we could be looking at something like this. So that's what we're looking at when we talk about our inflection points. So any questions about that? All right, so let me do an example on this. So in the previous section, we looked at where F was increasing or decreasing. Now we're looking at where F prime is increasing or decreasing. And we're going to do that using the second derivative. So let's say we have this. So let's say you're going to describe the concavity and however many inflection points there might be for this function. Well, first off, we're going to use our second derivative test. And this is going to be for concavity. And again, the reason we're interested in finding concavity, we're ultimately going to use it to find minimums and maximums. We're going to be looking for these extrema. So if we take the second derivative, I'll just sort of cut to the chase. We're going to get this. So what we want to do is we want to try to find out either where this equals 0 or where it doesn't exist. Well, it doesn't ever equal 0. Now, the way you could kind of play with this is you can, well, you can, no, here, let me show you the graph. This is actually going to probably help best. If you were to, let's see, if you did a graph on this, well, it should be 0. Let me take a look. You're dealing with a multiple of 1 over x to the 1/3. That's what I'm looking at. So x to the 1/3, this is only 0 when x is 0, just this part right here. But because it's in the denominator, if you put x to 0, you're going to get division by 0. So what that's going to mean, it does fail to exist at x equals 0. In that case, that one doesn't go. So what we end up getting is that we have a point of inflection at x equals 0. So again, there's nothing you can put in for x here that's going to zero this thing out. You would need like an x up here, for example, and something times this 0 is not going to work. And so we got x down here instead. So with division by x, or a power of x, well, what's going to make this 0? Well, it's just going to be 0. So that tells us we've got an inflection point at x equals 0. So let's take a look at this. Let's do a graph. And just like with increasing and decreasing using the first derivative test, we're going to choose test points. And I say go with something kind of easy. Say 1 and -1. And we're going to look at what the second derivative is doing. So if we plug in -1, need a little more room here. f double prime of -1 will be 10 over -1 to the 1/3. Cube root of -1 is just -1. You get -10 over 9. But the key thing, it's going to be less than 0. So here we're undefined. I'll put a big U here. And we're going to have negative for that interval. Let's see what's going on over here. I want to take it for granted that it's going to automatically go, say, positive. We can do the calculation. So f double prime of 1, this will be 10 over 9, 1 to the 1/3, or 10 over 9. And key thing here, it's bigger than 0. So that means this is positive for this side of 0. So what this tells us is this. Because the second derivative is negative on this side of 0, concave down. It's positive here, it's concave up. And this here, where in this case, f double prime of x is undefined, that's your transition point or your inflection point between the two concavities. And if you were to draw this, what this looks like, this function, is you're going to get something like this. You get something like that. And this is going to be your inflection point. Now remember, keep in mind, the inflection point, or the second derivative, is what's undefined here. The original function was this. It's when you take the second derivative that you get that x to the 1/3 in the denominator, and that gives you a division by 0. But the original function, there's no possibility for that, so it is defined there. It's the second derivative that isn't defined there. Any questions about that? All right. So what this brings us to, and this is kind of we've been sort of dancing around this. Let's actually just get to the point. The second derivative test for local extrema. And it's going to work like this. You sort of notice that as things are concave down, there's a maximum somewhere over here. And if they're concave up, there's a minimum somewhere here. And so we're going to get to that point. We're going to finally tie those two ideas together. If, now we're going to make sure, let me put some preliminaries here. So we want f double prime is continuous on open interval containing x equals c. So we've got an open interval. F double prime is continuous. It exists. And we're going to take a look at what's happening at some point x equals c. So if f prime of c equals 0. Now remember, f prime of c being 0 means that we have a horizontal tangent line. You get that at a minimum or at a maximum. And f double prime of c is less than 0, then x equals c is a local max. So what that's going to look like so let's say we have our open interval I here. And here's C. So sure enough, horizontal tangent line, f double prime equals 0. Oh, sorry, f prime of x, or c equals 0. And on interval I, f double prime of x is less than 0 for all x in I. So that's what we're looking at. We're going to choose, we're going to find where this has a first derivative of 0, and then we're going to look and determine, is this concave up or concave down on this interval I? And if it's concave down, I'm going to abbreviate that. It's concave down. I've seen somebody do that before. And we have the tangent slope at the same point C equal to 0. This means we have a max. So, and then we're going to have a min much the same way. If f prime of c equals 0 and f double prime of c is greater than 0, x equals c is a local minimum. It's going to be the same idea. So there's your I, there's C, there's the horizontal tangent line, f prime of c is equal to 0. And what's happening here, f double prime of x is greater than 0 for all x in I, including that point C, and that's concave up, CCU. So any questions about that? All right, so we got 2 minutes left. I don't think we have enough time to continue. Well, I'm going to continue. I'm going to finish this section. If you have to go to another class, because we got to, if you have to go to another class, go ahead. What I'm going to do, I'm going to go through an example on how to use this to graph a function. And then that'll be it. And then that'll finish us up for section 4.4. And that'll be it for today. So if you do have another class, don't worry, I'm recording this. So you can go to that class, and I'll post this video shortly. But let's use this. Let's put this to use. So we're going to graph y equals f of x. And we're going to use 7 steps. So first off, we want to identify the domain and any symmetries. Two, we want to find y prime and y double prime. 3, we want to find critical points. That's where the first derivative is 0 or undefined. And describe behavior. And let's see, we want to find where f of x, or just y, increases, decreases. Then we want to find inflection points. That's where the second derivative is 0 or undefined. And then use those to find, well, give us our transition, and it'll help us find concavity. So we're really going to be looking at the sign of our second derivative. That's going to be the big thing for us on that. So it'll help determine where we want to look, like test points and things like that. Identify asymptotes. These could be vertical, they could be horizontal. And finally, we want to plot any key points. And for example, intercepts. So we're going to use these 7 steps to graph a function. And one of the advantages, again, we have with calculus over algebra is that for precisely locating minimums and maximums, calculus is great. Algebra, we could kind of estimate where they were going to be. With calculus, we can get it exactly. So let's do an example. So let's say we're going to do this. So if we take a look at this, step one, domain. If we take a look at the domain in this one, well, there's no way this can ever become 0. Because if you try to set it equal to 0, you'll get x squared is equal to -1. And you're going to get x plus or minus neg square root -1, which is plus or minus I. And we're only dealing with real numbers in this class. We're not dealing with i's. So we can't use I for x. So there's no real value of x. It's going to make this 0. So the domain, it's all real numbers. Now, complex numbers, different story, but we're only dealing with real numbers in this case. So that takes care of our domain. Now, for symmetries, we can do our test for symmetry. And this comes from, and they make a little note in the text here, section 1.1. Let's see what f of -x produces. Now remember, f of -x, if the negative just disappears, this is symmetric about the y-axis. But if the negative passes through, this is symmetric about the origin. And again, this just kind of helps you graph the function. So you know it needs to look what it looks like on one side of the y-axis. It needs to be a reflection of itself on the other side of the y-axis. So, and then a reflection across the origin. If you have, say, x negative y, you're going to have negative xy as a point on there. Or let's see, I'm sorry, you'll have negative, if you have negative, if you have xy on your graph for the origin, you'll have negative x, negative y also on your graph if you're symmetric about the origin. But if we try this out, f of -x, what we get is -x plus 1 squared over 1 plus -x squared. Or we get this 1 minus x squared over 1 plus x squared. The square gets rid of the minus. This is not equal to the original function, f of x. It's not equal to negative f of x. Negative f of x would be something like this. We could move the negative down here. We'll get x plus 1 squared over -1 minus x squared. Move it down and distribute it through, and we'll get this, which is not the same as this. So what we end up finding, putting it sort of all together, f of -x does not equal f of x. It also doesn't equal negative f of x. So that means this function is not symmetric across the y-axis, it's not symmetric across the origin. So there's no symmetry. We do know the domain, but there's no symmetry. So we don't have to worry about that. Well, it's not something to really worry about. Just, again, it helps you graph. So let's dig in here. Let's find f prime of x, or y prime. If we hammer that out, what we're going to get, I'm just going to, for the sake of time, I'll just put it here. F prime of x is going to turn out to be this. And then f double prime, and you're going to be using a quotient rule on both of these calculations. You're going to get this. So now we have our derivatives. We can use this to find critical points. We'll use this to find inflection points. So critical points where this is 0 or undefined, inflection points where this is 0 or undefined. So taking a look at critical points first. So f prime of x, which was 2, 1 minus x squared squared, over 1 plus x squared squared. I'm going to set this equal to 0. And where this is going to be equal to 0, it's going to be x is plus or minus 1. Now, the reason is this can never be 0. And if it was, I mean, you'd have division by 0. But again, with this 1 plus x squared, it'll never be equal to 0. So that means only the numerator can become 0. So we got to set the numerator equal to 0. And if you solve for x, and here, I'll run through it real quick here. Again, if you have to leave, go ahead. I don't want to chase you away, but I mean, I don't want you to miss anything because this is kind of a long example. Divide by 2, you'll get 1 minus x squared squared equals 0. Square root both sides. 1 minus x squared is, well, plus or minus 0 is 0. Add x squared to both sides. And again, we only need to do the numerator. And then you'll get plus or minus 1 is equal to x. So that's where the critical points are occurring, plus or minus 1. So what this tells us is that we want to look at the behavior of these critical points. Well, we know they cause f prime of x to be 0. Now, if we take a look at the second derivative, f prime of minus 1, I'll put the plus or minus 1 in here. Either one will make f prime 0. You plug this into the second derivative, you'll get 1, which is greater than 0. So when that's positive, concave up. If we plug in 1, we're going to get negative 1, which is less than 0. That's concave down. So concave up means we actually could have a minimum. And this is going to suggest that we have a maximum. So let's take a look. Number 4, increasing and decreasing. So to figure out increasing and decreasing, again, we're going to take a look at our first derivative. That's going to be the key for increasing or decreasing. And we know it's 0 at -1 and 1. So again, what we could do, we could use test points. So I'd say recommend 0 to try to keep it simple. And if we take a look at f prime of 2, what we're going to get, let me pull up my function here. 2 times 1 minus 2 squared over 1 plus 2 squared. So we'll get -3 squared is 9. We'll get 18 over 9. And that's going to be 2, which is greater than 0. So that's going to tell us this is positive. Now, if we take a look, f prime of 0, we'll get 2, 1 minus 0 squared, 1 plus 0 squared. We'll get 2 over 1, which is again going to be 2, which is going to be greater than 0. So that means we've got positive again. And then finally, try -2. So let's see, we'll get -3 squared. It's going to be 9, 2 is 18. We're going to get the same thing as we had before, a little different here. It's going to be 4. Oh, I might have made an arithmetic mistake, but it's going to be, it's not going to matter because we're going to basically want to know if we have positive or negative. So -2 squared is 4, plus 1 is going to be 5 squared. That's 25. But still, it's greater than 0. This one would be 18 over 25 also, but instead of 2. But this is what we're going to get. So for the first derivative, it's always increasing. Well, it levels off at -1 and 1, and then it increases again and again. So that's our increasing and decreasing. Let's see here. Oh, shoot, I made a mistake. All right, I better cut it off here. I'm trying to push something faster than I should. I apologize. I made a mistake. I'm copying the wrong, I'm putting an extra square where there shouldn't be. So let me repost this example. I'm trying to push this too fast. I apologize. And I made a little arithmetic error. So if I'm making an error like that, I better call it now. I'll do the example and post it tonight so you can see it. And then what I might do instead, I will save it for class next time. Let's do it together. Because I know I'm going way over time and I'm concerned this isn't going to be very effective. So I'm going to back off. We'll come back to this example. We'll do it in class on Wednesday and we'll go from there. I apologize. I had an extra square that was making things not work. So that's going to be it for today. We'll go over this example on Wednesday. Other than that, have a wonderful afternoon.
Hi,